Good afternoon, this is Schweitzer, and we're going to run through some problems involving projectile motion. This is maybe about as advanced as we would get in our physics class. So if a car is driving along at 10 meters per second, so we'll draw a picture of this. We have ourselves a car. Let's say it's traveling to the right at 10 meters per second, and it launches. I don't know, maybe it's got some sort of little cannon on the front here. It launches at 60 degrees to the horizon at 17 meters per second, some object, and that object will then take a projectile motion. The question is then how far down the line will it go, how high would it be, so on and so forth. So in this case, let's just start answering these questions. Number one says, how long will the object be in the air? So before I do this, I'm going to take my triangle, and I got angle 60 degrees, 17. So I'm going to get my two vectors. I got my x component is the cosine of 60 degrees times 17 equals. The y component is the sine of 60 degrees times 17 equals. And of course the car itself is moving and in the x direction at 10. So let's run this math through here. 17 times the cosine of 60 equals 8.5 meters per second. This 17 times the sine of 60 equals 14.7. And then at this point we're also moving in the x direction an additional 10 meters per second. So just be aware the x total is 18.5 meters per second. Alright, so how long will the object be in the air? That's controlled by the y-axis. So at this point, question number one, I'm going to look for when my object creates, I'm going to erase this, I'm going to treat it just like it's in the y, so it's going to go straight up and come down. It's the y component. That's all I'm worried about. Even though it does go like this, I'm thinking it's as if an object went straight up to the same height and then came back down. Alright, so in this situation, velocity final equals velocity initial plus AT. Velocity final is 0. Velocity initial in the y is 14.7 plus AT, which is negative 9.8 times your time, and this is going to be time to get to the top. So and t equals 1.5 seconds. So we have 1.50 seconds up, and technically another 1.50 seconds on the way down, for a total path time of 3.0 seconds. How high will the object get? Okay, number two, again, the height is determined by the y-axis only. So distance traveled equals initial location plus velocity initial times time plus 1/2 AT squared. This is a number that we don't know. 0 plus velocity initial, which is 14.7. I'm only going to include the 1.5 times because that is the time at its max height. In this case right here. So at this point, okay, we got plus 1/2 and the negative 9.8 times the 1.5 squared. And let's do the math here. 14.7 times 1.5 equals 22.05 minus 11.0, and we'll do that subtraction. Ends up being just about exactly half of it. In this case, 11.05. That's it. The distance equals 11.05 meters high. The next question, it says, number 3, how far away will the object land? This is going to be determined by the x component. Alright, so now keep in mind that this thing is traveling in the x direction 18 meters per second, 18.5 meters per second. So distance equals xi plus vit plus 1/2 at squared. Distance traveled is what we are looking for, equals 0 plus 18.5. Now, I don't want to know, if I wanted to know the distance on the ground it would travel at 1.5 seconds, that it would be at its maximum height at that point. So I don't want to use, if I want to know how high it would be at that point, or say, if I use the 1.5, that would give me the distance traveled at 1.5, which consequently is also the time of its max height. I want to know when it hits the ground. That means I got to use the full 1.5 plus 3 seconds. And then plus 1/2, and then there's no deceleration in the x components. That's gone. Just going to be 18.5 times 3 equals 55.5 meters. And that's how far down the road it would actually land. So the next question says, okay, it says number 4, true, false. The object would be in the air the same amount of time if the car is not moving. That is true. The time in the air is controlled by the y component, and the car is only moving in the x component. So these two are not affected by each other. True or false, the object would go higher as the car travels faster. Again, that would be false. How high it goes is controlled by the y component, and the car moving faster is moving in the x component, so that would not matter. The object would land is going to land farther away because of the car moving. So this 55 meters is landing farther away because the car is also adding a push to that object. So 4 and 5 are done. Okay, so let's look at this now. What is the object's velocity and angle of impact? Okay, so in this case, we want to look at this is I think 6. So what is the velocity in the x component? What's the velocity in the y component? And then we'll find our correlating component between these two. X component is going to be 18. The horizontal never changes. It's 18.5 meters per second. The y component, the ball is going to be going up, and then it's going to be coming down. It'll be 0 at the top, and it would be at max velocity at the bottom. So you can calculate if you want. You could just use the VF formula. VF equals VI plus AT. This would be what we would solve for. Initial velocity is given at my angle 14.7, and then plus the negative 9.8, and I want to know what it is right here, which is at 3 seconds, and you would find out that the answer is negative 14.7. So whatever it left with is what it comes down with, so it's going to be negative 14.7 at this point. Let's see what we got here. So it's going to be, I'm going to use my Pythagorean theorem, so it's going to be 18 18.5 squared plus 14.7 squared equals the hypotenuse squared. So 18.5 squared plus 14.7 squared equals the square root of this answer, and this is 23.6. So the answer is 23.6 meters per second. Okay, and then at that point we can use a trig function in order to figure out the angle here. So I'm going to use my sine function. So the sine of the angle is equal to the opposite over the, let's say, hypotenuse. Okay, so the actual angle is equal to the inverse sine of the opposite over the hypotenuse, which is equal to, let's see, opposite is going to be 14.7 divided by 23.6, and then we'll plug that whole value in here. Second sine 14.7 divided by 23.6, and the answer is 38 degrees. Alright. Keep in mind that where our normal angle here would have been 60 degrees. Well, that's what we left at. But now we're only at 38 degrees because the object is moving. So if it wasn't moving on a typical projectile motion, it would be the same on both sides. But you know, if we're throwing off a cliff as well, it's not, you know, then you gotta be able to calculate. Use your x component, use your y component, and solve for your angle. Other than that, I think that's the last question. All right, thank you very much.